A good thermal camera is useful to have in the lab. We invested in a high quality unit from Testo to support our high power GaN amplifier module development work. We initially thought it would be useful in allowing us to monitor the temperature of the GaN devices. Whilst it does this as well as we had anticipated, we have also found it to be a very useful diagnostic and analysis tool for other circuitry. We'll go down into our lab now and look at the thermal camera in action.
Okay, we're here in the PRFI lab, and we're going to use the thermal camera on an EVB of a GaN device, which is the sort of usual thing that you would do in the lab, the sort of general thing, looking at the temperature rise of the device. So if we move over to the view from the thermal camera, I'll switch the device on. So switch on the gate bias and the drain. So it's just warming up now with the quiescent power of around about 10 watts running. You can see the image is starting to increase in temperature. The dark areas on the image are the metal areas, which are acting as reflectors. So they look bright in optical, but in the infrared that we're looking at here, they look dark because they're reflecting colder temperature things. The warmer areas, so you can see the device up at about 28 degrees in the center of the image. That's the area of the board that it's not reflective, it's emissive. So we'll switch on some RF as well now, and I'll increase the power. So I'm going to go up to around about 5 to 7 watts there. So you can start seeing that the whole of the image is increasing in temperature. So it's up at 33, 34 now. And we can leave this on for some while and it'll all get up to the same sort of average temperature. Obviously the device itself, which is it's a packaged device, we can't see the surface of the GaN chip, and that'll be much warmer than that, and you need some very specialist equipment to actually look at the temperature of the channel. But yeah, you can see there, so getting up to around about 40 now. So there's around about, as I say, 7 or 8 watts coming out of the device, and the actual DC power going in is about 30 watts. So around about 20 watts dissipated. Another application that we've got for the camera is to look at passive components rather than just the active components, where we can see power dissipated in them. One thing in particular for this application, we need external bias tees for this device. So we're looking at a choke to go on the drain. It's a ferrite choke, so it's got to pass the DC to bias up the drain. And we found a device, but in fact we put that onto a PCB between two SMAs, measured the S parameters. You could see loss in the line, but a bit of extra loss due to the device showing ripple. So we wanted to have a look at this, see what effect RF would have on the device. So we mounted it in shunt between ground and the transmission line. So if I switch on the device again, we've got it set up to take around about 7 watts again, which is what we want from this device. And you can see on the image here, the room temperature, it starts out around about 27, the device, and you can see it warming up there pretty quickly as we pass the power through it. So it's a 50 ohm transmission line that the device is mounted on in shunt to ground, and you can see that it's the end closest to the RF line where we're dissipating power initially. So it's lossy ferrite with wire wrapped around it. So it can be quite important to know that you've got extra power dissipated, not just due to the DC bias that's going to be passing through the device, which could be a couple of amps, which will increase the temperature, but also RF is getting into the device and causing heating as well.
We've also found the thermal camera useful for ensuring that the power dissipated on boards we've designed is acceptable. On this PCB, which is a support board for one of our PA modules, we know that there is a Zener diode which will be dissipating a reasonable level of DC power when the board is unloaded, in other words not attached to the accompanying PA. So we took precautions with the PCB layout to provide heat spreading to conduct heat away from the component and so minimise its temperature rise. So here's the support PCB wired up into its test circuit, and again, as I said, it's unloaded. The Zener diode that we're going to look at is here. So we're now going to switch over to the infrared image, and now we're going to turn on the power. Now you can see the component has started to heat up and it's settling at around about 55 degrees centigrade. And it's certainly the hottest part of the board, but this is acceptable for the board in the unloaded state, and it shows that the heat spreading is effective. Here is another of our PA support boards, but this one has a fault where a resistor is running slightly hotter than it should be. If we now look at the thermal image, you can see indeed the component is running hot, and when we looked back at this board we found that there was indeed a component with the wrong value of resistance set in there.